Tonight on Unsolved Algorithms.
Public transportation. Why is the efficiency so bad?
Look at this. Costs. Why are they so bad? Budget costs.
Why is this guy asleep? Where's his bus?
Find out tonight on Unsolved Algorithms.
Before we can iterate over our case studies, it's important to know how genetic algorithms work. A genetic algorithm works such that we take a known problem, and its variables are set as follows. Constant variables remain constant. Testable variables are ones you will set as mutable variables. They should be small so they can test them without a huge impact to the actual set. Then you run it. You run it a lot. It'll give you a bunch of solutions. The first one being the original, and then it'll continue building solutions from that. The successful solutions, the ones that are quicker, go into a solutions pool. And continuous runs choose from the solutions pool in what's called a crossover, where it takes a parent 1 and parent 2, mixes a small portion of each one, and runs it again. If it's successful, it goes into a solution pool.
Metro systems are one of the main sources of public transport, and it consumes a high track of energy daily. So methods for metros to run energy efficient are very sought after. The authors of this article designed an algorithm for energy efficiency that can be broken down into two parts. First part, the timetable optimization. There are n periods of dwell time. Dwell time is when the metro bus stops for people to get on or get off. And we have m trains. So what we're going to do is we're going to set this value k equal to n times m. So to solve this equation, what we're actually going to use is a genetic algorithm made called the mixed integer lattice crossover power mutation, which will modify the dwell time at each stop to make full use of the regenerative energy. Okay, the second subproblem, we have the compensational driving strategy algorithm. So what this does is when a disturbance happens for the metro, say too many people are getting on at once, or somebody's shirt gets stuck in the metro door, terrible things. But what this does is tells the next metro, hey, we're gonna take a little bit longer, slow down, wait a couple real-time seconds. So what we do is we check if there's delay in the bus beforehand. If there is, we calculate this, basically the time it takes, or the time it's taking for them to wait, and then eventually apply this to the next bus. This algorithm was tested on the Shanghai Metro Line 1, which they were able to use a 4-train system traveling 6 stations. Results are positive, showing the trains saved 5.12% during TO, 4.04% during CDSA. Here's a CDSA, the last graph was TO.
A negative aspect to the algorithm is that the infrastructure changes required are not cost-effective on small metros like Buffalo.
The second case study is design of the public transport lines with the use of a fast genetic algorithm. In this, they took the problem of small cities. As they get bigger, the wait times go from small to large, longer. And the happiness of the city goes from awesome to this guy over here who's not quite sad. So, they took previous algorithms which didn't use this, and they were slow, so forever. They were NP hard. To do that, we used a genetic algorithm, which has 3 constants: the number of buses, the bus capacity, and a directed graph that has the vertices of the bus stops and edges of possible stops from each stop. Then there's mutations, which are small changes. The number of communications lines, the shape of them, the direction of them, the buses are located to each line, and the waiting times at each stop for that line. To simplify the genetic algorithm, to make it from NP hard to something reasonable, they decided to forego the precise determination of bus arrival time, which gets increasingly hard as cities grow, the number of buses and stops increase. It's just impossible to do. So, they decided it was more important to find the interval time between 2 successive departures and make it consistent. This allowed the creation of channels, which has a certain bus capacity and the specific times driving to the next stop. This allowed them to use Dijkstra's algorithm to find the most promising channel at any moment during the bus's stops. Well, we're done. And what is our result? Well, the result we want is to reduce the calculation times of our solutions. A simple case of this took 20 stops and 20 buses, reducing time from a full algorithm of 9 hours to 1 hour with the fast algorithm. This is a map of the stops, and this is a graph of the compute time. The Sicilian city of Katowice used the case study in their bus lines to reduce the time from 320 minutes to 152. And in case for this, negative to this algorithm is since it's given to local companies, they can use the algorithm to compute a faster time between stops just for their clients.